Okay.
We're gonna do it in like okay. You can title it, guys, related rates,
But it already kind of says that at the top of your yellow sheet. Okay, so listen up. Okay, today, I don't know if you'll be confused or not. We'll see. Okay, the bad news is that since you don't have school tomorrow, we need to really try to make this solidified because on Wednesday, these examples will get harder. Yes? We're not going to glue them in an order. Now, if you hate cutting and pasting, we're going to do this every day all week. So fun. But if you hate it, listen. Or if you already write slow and then you cut slow and then you glue slow, you can just write number one in your notes. It's supposed to be kind of like fun to cut and paste.
It's not fun.
Kind of fun, you know? Okay, but if that doesn't feel fun, then you can just number it and do it in your spiral. Okay? That is what's up. Yeah, today I already tricked you into doing it, but on Wednesday... Okay, here is what related rates are. It already says it on here for you. It's the study of applied change. Okay, the only reason that most people don't like this is because it's word problems and most y'all don't like reading. Okay, but, it's okay. Here's an example of what you're going to be doing in related rates. Let's say that you know how fast the side of a cube is changing, and then you want to know how fast the area is changing. Okay, they're both rates, and they're related to each other, yeah? Okay, another example. Let's say that you have a guy over here, and a guy over here, and they're walking apart from each other, and you want to know how fast the distance from them is changing. Okay, it's very physicsy, vectory, that kind of stuff. But it won't be as complicated as what you see usually in physics, okay? So, first thing that I'd like for you to do is we're going to do some basic derivatives of related rates. So, number one. We're going to glue them as we go. No, we're not doing one of those. I'm just going to we're going to do little short notes first. Okay, so first thing I would like for you to practice is taking the derivative with respect to time of random equations, okay? So the first one that we're going to do is going to be the volume of a sphere. 4/3 pi r cubed. Okay, the second one we're going to do is going to be, let's stick with circles. The area of a circle is pi r squared. Okay, here we go. When you take the derivative in related rates, you are going to be taking the derivative with respect to time. So any variable that is not a t for time, it's going to leave a d, that letter, dt at the end. This is what I mean by that. When I take the derivative of a, what's the derivative of x usually? So the derivative of a would be 1 dA dt. Okay? dA dt. Okay, now come over to your pi r squared. That's the r's leg. Okay? How do I take the derivative? I take the 2, times it down to the front, so now it's a 2 special magical pi, okay, for you. And then r was squared, now it's to the what? 1. Then what do I have to put at the end because it wasn't a t? D r dt. So whatever the letter is in your equation, when you take the derivative of it, you have to put a d, that letter, dt. Okay, come over to your volume 1. What's the derivative of v? dv dt. Good. Okay. Then on the other side, I'm going to take my 3, I'm going to multiply it down What is 3 times 4/3? Okay, just 4, right? Because what happens, you have a 3 on top, you have a 3 on bottom, they cross out, yeah? So it'd be 4 pi. What is the new power on r? It used to be cubed. Squared. Then what do I put at the end if my letter was an r? dr dt. Okay, let's do 2 more. Number 3. Let's do the equation volume equals side cubed. So this would be like for a cube. What's the derivative of v? dv dt. What's the derivative of s cubed? 3s squared, then what? ds dt. Very good. Okay? Last formula that I'm thinking of is circumference. I'm not very creative. Okay, 2 pi r. Okay, what's the derivative of c for circumference? dc dt. What's the derivative of 2 pi r? Remember, this is an r to the 1. So I would do my 1 multiplies down on the 2 pi. So it will stay at 2 pi. And then what happens to my r if it was to the 1? Now it's to the 0. Right? It was to the 1. Now it's to the 0. Then what do I put at the end? dr dt. Good. So remember, when I take away 1 from 1, I get r to the 0. So even though the r goes away, you still have to put a dr dt on the end. Now, this should be a little familiar to you. Do you remember when we were doing d dx, and whenever we did it on a y, we had to add a dy dx? It's the same thing, but instead of d dx, it's d dt. So t is the only letter that doesn't have to have a d letter dt on it. Yes, ma'am? Do you have to write the pi, what? Okay, I did it because he made fun of he said my pie had 3 legs, so I was trying to make like a curlier pie, but if you do straight or curly, it doesn't matter. Alright, now, look up at your little square. It does look like it had 3 legs, but it's a pi and then an r, you know? Okay? Alright. So, look up at the top. I'm going to walk you through some stuff that's probably not going to make a lot of sense until we start doing questions. I can, yes?
Wait, wouldn't it not be r squared, 2 pi and r squared?
Are you talking about here? No, because you take away 1. So if that was an r to the 1, when I'm...
R to the 1?
That's a 1.
Oh, no, that was 3.
Yeah, that's a 1. Some of them are cubes, some of them are just 1s. Is my handwriting bad?
No.
Oh, wait.
Good.
Yeah, I'm missing 1 contact.
Okay. Alright, so look at the top. Okay, dq dt, right here, represents the rate that q is changing with respect to time. This is what that means. dv dt is the rate that volume is changing. Okay, what is dr dt? The rate that the radius is changing. What would ds dt be? The rate that the side is changing. Okay, now, 2 more really important things. If your ddt is greater than 0, that means that q is increasing. Now think about dq dt is the slope. So if I have a positive slope, does it make sense that my q is increasing? Yes. Okay, then come over here. If my q is less than 0, then that means that my q is decreasing. Because remember, this is a slope. If it's a derivative, it's a slope. So we should already kind of sort of know that from all the first derivative test stuff. Okay, so right here, this is how we're always going to start with questions, is find, given, when, and equation. So I want you, the first question we're going to glue in is the one about the pebble. You should have hopefully already cut them out, and you're going to glue that one in as number 1. So it says a pebble drops into a pond, causing ripples in the form of concentric circles. And then you're gonna just glue it in. And then if you hate gluing the rest of the week, you can just not do it. I guess I don't care. This one right here. A pebble drops into a pond. Wherever, if you only have a little bit of space, I'd go to the next page. Okay, so once you have it glued in, I want you to write F for find, G for given, W for when, just like you had on your notes. Find, given, when, an equation. Now, usually I'm not going to label these with words just because it makes it take forever, okay, but on the first one I'm going to. So F is find, given, when, and equation. Okay. A pebble drops into a pond, causing ripples in the form of concentric circles. The radius r of the outer ripple increases at a rate of 2 feet per second. When the radius of the outer ripple is 4 feet, at what rate is the area of the outer circle of the disturbed water changing? Okay, so we have a ripple in the water. Okay, here's the radius of the ripple. What is happening to the radius of the ripple? It's doing what? It's increasing. Do we know how fast it's increasing? 2 feet per second, then that's my given. dr dt is 2 feet per second. Okay, next, I want to find the rate that the area of the water is changing. I'm going to find dA dt, where A will be the area of the water inside the ripple. So my equation is going to be area equals pi r squared. Now let's look for our when. Okay, did it say when the radius of the ripple is what? 4 feet. Now let's go back and look at your first little sheet with your steps on it just to kind of connect the dots here. So it says, find, this is usually a rate, so we were looking for dA dt. So the Q on here is generic for like any quantity, okay? So we're finding dA dt, this is what we want. Our given is a rate, and then look what I put here. Consider the sign. Positive means it's increasing, negative means it's decreasing. So if my ripple is growing, is it appropriate that we have a positive 2? Yes, because it's increasing. Okay, then it says for my when, it's a particular measurement for something that's changing. My radius is growing, but I care about when it's 4. Does that make sense? That's like your time, kind of. Okay, and then your equation has to relate those guys together. Okay, the next step, you are going to take the derivative on both sides with respect to time. This is what we just practiced. So what is the derivative of A? dA dt. So now I'm taking the derivative. We already did pi r squared, but let's review. We times the 2 down. So now it's a 2 pi r. And then what do I put at the end? dr dt. Then from there, I'm going to plug in what I know, solve for what I don't know. This is the last step. Look right here. Okay, it says solve for any remaining unknowns. So let's plug in what we know. What is dA dt here? That's what we're trying to find. 2 pi r. What is my r? 2. Now I'm going to use units on the first couple of these. I'm not going to do it on all of them, but just on some of them. So my R is 2, oh wait, hold on. Crap, no, my R wasn't 2, what was it? 4. So I have these backwards, but since we're multiplying, it doesn't really matter. So I have 2 pi, my R is 4 feet, my dr dt is 2 feet per second. Sorry that I wrote those backwards. Okay, now, everybody good to there? Okay, let's multiply. What is 2 times 2 times 4 again? 16 pi. Now let's talk about units. I had feet per second times feet again. Feet squared per second. Now question, if I'm measuring how fast the area is changing, does it make sense that I got feet squared per second? Does feet squared measure area? Yes. Okay? So you would say the area of the circle is increasing at 16 pi feet squared each second. You do not need to write this out again. Just since we're kind of starting off, I'm trying to connect the dots here. So that's what that means, is that the area of the circle is increasing at 16 pi feet squared each second. Now, on your homework or something, you don't have to write that sentence. That's just for right now to try to help you understand what you're finding. Okay, next one that we're going to do is going to be a spherical ball is inflated. That one. A spherical ball is inflated with, it should say air, at a rate of 800 cubic centimeters per minute. Okay, and that's your answer and you're done. Yeah, on that one. So that's the one that you're gluing in next. A spherical ball is inflated at a rate of 800. Probably not. Second period, I think we got through all of them except for like 4, but they have a longer class than y'all, so. Because of the announcements.
Spherical ball.
Yeah.
The second one go up. I just cut them out and like scrambled them over there. It's not. For me, it was.
Okay, so I'm going to read it to you while you're cutting. I want you to try to listen for the find, the given, and the when. Okay, a spherical ball is inflated, it should say with air, at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant when the radius is 40? Okay, what are we trying to find? How fast is the radius of the ball changing? What is our find? dr dt is correct. Because it's how fast the radius is changing. dr dt. Okay, now, what is our when? It says right here, when the radius is 40. So when radius equals 40, I'm going to label it also with a centimeters. Okay, now let's go back to our given. It says the ball is inflated at a rate of 800 cubic centimeters per minute. If they're measuring how fast they're inflating it, they're telling you how fast the space inside it is changing. What is that called? Volume. Yeah? Because it's how much air is in the balloon. So this is volume. Now, your other big hint on that is that it's cubic centimeters. Anything cubed is usually going to be volume. Okay, so dVdt, it says it's being inflated at 800 centimeters cubed per minute. Okay, now the equation for a sphere is 4/3 pi r cubed. So take the derivative. We already did it once, but try to do it without going back. Okay, what's the derivative of v? dv dt, good. And then on the other side, I would times the 3 down on the 4/3. What's 3 times 4/3? Just a 4, because the 3's cross out. Pi r squared. And then dr dt. Okay, then looking at that, I want to plug in my knowns and solve for my unknown. So, dv dt, I know. What is dv dt here? 800 cubic centimeters per minute equals 4 pi. And then my r is how many? 40 centimeters, right? Squared. And then my dr dt is what I don't know. So what we're going to do is we're going to multiply this stuff together, and then we're going to solve and divide to get rid of it. Yeah? So what is 40 if we square it? 1600, right? And then I'm going to times it by 4. So that'd be 6400 pi. Now let's talk about units for a second. It was centimeters, but then I squared them. So centimeters squared times dr dt. Then on the other side we have 800 centimeters cubed per minute. So I multiplied my green circle together. Okay, I got 6400 pi centimeters squared dr dt. I'm going to now divide by this on both sides. So 6400 pi centimeters squared, 6400 pi centimeters squared. Then what's going to happen on the right side? I solved for what? Just my dr dt is left over, good. It would be 1 over 8 pi, very good. Now let's talk about units for a second. I had centimeters cubed, I divided by centimeters squared. So what would be left here? Centimeters left over per minute. Okay, now think about, does it make sense if my ball is inflating that my dr dt came out to be positive? Yeah, because as my ball inflates, my radius is going to have to grow with it. Okay? Make sense? Okay, let's go to part B. That was part A. Part B on the same question says, how fast is the surface area of the balloon changing at the when the radius is 40? So come down here, find given when. What are we finding? Yes, so what would we put if we want how fast the surface area is changing?
V equals S.
Because it's area, yeah? Okay, so we're trying to find how fast the area is changing. And then our given, I'm just going to put part A. Okay, because all of our part A stuff still applies here. Now, what's our when? When the radius is 40 centimeters. So that's good because that's the same time that we were already looking at in the previous part. Okay, the equation for surface area. Area equals pi r squared.
Wait, then what does S mean?
S and A are the same, surface area.
No, like V equals S cubed.
Oh, that's side, that's for cube. Usually you would use A for surface area. But okay, from here, take the derivative and then plug prep in. So what's the derivative of A? D A dt, right? Then on the other side, my 2 is going to multiply down on my 4 pi. Now it's an 8 pi. R was squared. Now it's an r to the 1. Then times by dr dt. Okay, from here, dA dt, I'm going to leave it alone because I want to know that, but I don't have it. On the other side, I have 8 pi. What is my r? 40 centimeters. And then what is my dRdt? I found it in the previous question. 1 over 8 pi centimeters per minute. Okay, now let's think about our number here for a second. I have 8 pi times a 1 over 8 pi. What's going to happen here and here? Cancel out. Then really I just have 40 left as my answer. Now let's talk about units. I have centimeters multiplied by centimeters per minute. Centimeters squared per minute. Okay, now question, does that make sense for dAdt if I'm measuring area that I got square centimeters? Yes. Good. Okay, next one that we are going to do is going to be your grain silo, a cylindrical grain silo. That is the next one. It's about halfway down. If you left yours still in there. See, don't you like cutting and pasting? Oh, Deborah, I forgot to give you back your calculator. Okay, read through it. I want you to try to fill out your find, your given, and your when. Any part of that you can figure out. So a grain silo with a radius of 8 yards is being filled with grain. The amount of grain in the silo is increasing at a rate of 320 cubic yards per hour. How fast is the height of this grain in the silo increasing? Okay, what are we finding? dHdt, very good. It says, how fast is the height of the grain rising? Okay, what were we given? It says the amount of grain in the silo is increasing at 320 cubic yards per hour. What's that a measurement of if it's how much grain is in the silo?
Volume.
Good, dVdt. Okay, dVdt is 320 yards cubed per hour. Okay, then for my when, it never used the word when, so we're just going to put a little question mark. Okay, now, the equation for a cylinder is volume equals pi r squared times h. Now, if we were going to take the derivative of this right now, I have an r and an h, I would need to use what rule? Okay, it is still kind of implicit, but you'd have to use product rule. Now, that is if the radius and the height are both changing. Okay, think about our silo for a second. It says it's a cylinder, yeah? So here's our cylinder. Okay, as the grain comes in and the height of the grain goes up, is the height going to be changing?
Of the cylinder?
Of the grain in the silo?
Yes.
Yes. Will the radius of the cylinder be changing? No. Think about whether my grain is here or my grain is here, or say it's empty. What's the radius the whole time? The radius is 8. So I'm going to put right here a little star. Radius equals 8 is a fixed constant. It is not a variable. So you plug in r equals 8 before taking the derivative. Okay, if it is a fixed constant, you can plug that number into the equation first. But if it's changing, you have to wait. So instead of volume equals pi r squared h, I'm going to do volume equals pi 8 squared h. And what is 8 squared? 64 pi h. And then that's what I'm going to then take the derivative of. Okay? That is a squared. I feel like y'all are throwing shade today, huh? A little sassy over there. What's the derivative of v? dv dt. What's the derivative of 64 pi h? 64 pi, and then what? dh dt. Where did the h go? It was to the 1 power, so when I take 1 away, now it's to the 0 power, it goes away. Yeah? Okay, then we're plugging in which letter? dv dt is how many? 320. Yeah? So 320 yards cubed per hour. Now, I forgot when I plugged in the 8, what was 8 measured in? Yards, and then you remember how I had squared it? So I'm going to bring back in 64 pi, that should be yards squared, dh dt. Because when I squared my 8, there should have been a yards right here, if you want to write that in. Okay? So then from here, how would I solve for dh dt? What would I need to do with this? You would need to divide that on the other side. So I do divided by 64 pi yards squared, divide by 64 pi yards squared. These guys are going to cross out. dh dt equals 320 over 64 pi. Now let's talk about our units. I had yards cubed. I divided by yards squared. What would the result be? Yards per hour. And if I'm measuring the height of grain in the silo, would that be correct? Yes. Now, 320 over 64 is both divisible top and bottom by 8, but it doesn't matter, you can do it or not. Okay? Remember, if it's free response, you don't have to reduce. Okay, next one is going to be the fishy problem. Water pours into a fish tank. Okay, water pours into a rectangular fish tank at a rate of 3 cubic feet per minute. The base of the fish tank is 2 feet by 3 feet and it is 4 feet tall. How fast is the water level in the tank rising? Okay, what are we finding? How fast is the water level rising? Not volume. Water level is a measurement of height. Okay, so water level is height. So I'm going to find dh dt. Now, they told me how fast the fish tank is filling. That's a measurement of what? Cubic feet. That is volume, yeah? And then it says that it's filling, it's pouring into the tank, so that would be positive 3. feet per minute. Okay, then it says the base of the fish tank is 2 by 3 by 4 feet tall. Are those things that are changing? No. So rather than putting them as my when, I'm going to draw a picture. Okay, here's my fish tank. Okay, you have this little fish in here that is dying of needing water. Okay, maybe he has a little castle for fun. Okay, here's his water level. What aspects of the water are changing? Is the length or the width going to be changing? No. What are they the whole time? 2 and 3, right? So we'll say this is 2 feet, this is 3 feet. Okay, how tall is the fish tank? 4. Is that how tall the water is? Cross it out. Okay, we're not talking about how tall the tank is, we're talking about how tall the water is. So I'm going to label this with an H, because specifically we're talking about the height of the water. That's the height of the container. That doesn't help us. So when I plug into my equation, volume equals length times width times height. My length and my width are fixed. My height will be changing. So I'm going to plug in L equals 2 and W equals 3 because they are fixed constants. When you fill something up, the water is going to match the size of the container. Okay? So volume equals, what's 2 times 3 here? 6H. Okay, then just to try to hurry so we don't run out of time, what's the derivative of V? dV dt. What's the derivative of 6H? 6 dH dt. And then what is the dV dt for the volume? 3 equals 6 dH dt. Then when I solve for dH dt, what would I do with the 6? Divide it. Now, even though we kind of skipped out on units here, if we know that we're measuring height, it would be what? Feet per minute. Okay? So you know that if you divide volume, which is feet cubed, by feet squared, then you'd have feet left over. Okay? Alright, we will finish the rest of these on Wednesday, so don't lose them. And good job.